So there's been a ton of interest in building a pre-amplifier for the little Shortwave Crystal Set. We've got the loose coupler feature on the Crystal Set, which has been interesting to people. Works very slick. We do not want to lose that selectivity. So with this preamp, we're starting with a tube type preamp in this video. We'll go to a solid state preamp in the second video. We have a dual tube in a Cascode preamplifier, and I think you guys are going to like this project. It also uses the Faraday shield idea with the high Q hand wound inductors. So stand by, we're going to pep up your Crystal Set. We've got a Crystal Set that has some loose coupling on the front end, and it covers the shortwave bands pretty much from 49 meters all the way up to 16 meters, a little higher even, with one sweep of the dial. So people wanted to see an amplifier, a tuned radio frequency amplifier. In this case we'll call it a Preselector, that we can put in front of the Crystal Set to bring the sensitivity and selectivity up for the shortwave bands. Now, building preselectors for the shortwave bands is nothing new. Certainly hams have been doing it since time began, and I've got a lineup of tubes here that have been used through the ages to amplify signals. Here's a book called 101 Easy Ham Radio Projects, and of course they have a all-band preamp schematic here, which I'll show you. And the tube in that particular preamp can be almost anything. Of course, everybody knows about the 6BA6 or the 6BZ6 as being a hot front-end tube. In early days, the 6K7 and some special tubes from World War II that were specially selected for gain, such as the 1852 and this British tube. It's an EF50, very hot tube here. It's so hot it's painted red, and the EF50 was a super transconductance pentode. I'm going to go to an older radio amateur handbook. This one is from the wartime, actually pre-war, and they're showing the 1851 as a preselector. This is quite a device, and as you can see, this tube is so hot that they actually tap down the coils to give extra selectivity, and it's got shielding between the input and the output. This is a very fine preselector. It uses plug-in coils. There's lots out there. Even these tubes from the 30s, some of the early Pentodes and Tetrodes, would work fine in the circuit. We get into the 6K7 from the 30s, and we have the 6SK7, 6S7. We've got the 1U4 and 1U5 type pentodes and the battery types, and there's also gate charge types that take very low voltage. This one represents the 6BA6, 6BZ6, and so on. The 6AK5, probably the hottest miniature of the war, World War II. Sub-mini tubes came in the 50s, and even the pentode section of tubes like the 6GH8 and the 6U8 make fine shortwave preselectors or shortwave tuned radio frequency amplifiers. Guess what? We're not going to do this. There's too much that's been published building a single stage pentode type RF amplifier. 99% of all the RF amplifiers out there use something like this. So we're not going to do that. We're going to use a different circuit, something that's going to maybe give us some newer technology that came along during the war years rather than during the 20s and 30s. Now, as you can tell, in this first video we're concentrating on vacuum tube technology. The second video on shortwave preselectors is going to be completely solid state, So if you're not into the tube technology, maybe you can skip this one and wait for the solid state version. So this is 16 meters. Coming in, it's about 4 p.m. Yeah, it's going to be a little bit of evolution in the breadboarding style. We're going to actually put a ground plane down, and we're going to be soldering directly to that ground plane on this breadboard. That's because we're at a higher frequency. We're trying to amplify the shortwave frequencies, and the chances for feedback, oscillation, and instability are so great that we have to use a ground plane and build over it. So watch out for that stuff as we go along with this tube type preamp. So amplifiers, let's talk about the gain. How do you measure gain in an amplifier? The gain of any of these RF amplifiers that we're going to be discussing depends primarily on the plate load impedance. The higher the impedance, generally the higher the gain. Some compromises have to be made if we're going to transform this high impedance down to that usable value we need to feed the crystal set. It has a really low input impedance with that input link, the variable coupling input link. And this step down will directly reduce the voltage swing and thus the gain. When we're measuring gain, by the way, especially if we're simply measuring voltages like with 10x scope probes, we have to know the impedances. We have to know what the input impedance is and what the load impedance is. Otherwise, we're just kind of fooling ourselves and measuring just voltages. We would really like to measure power gain. And as you know, to measure power, we need to know either voltage and current or voltage and resistance. So measuring gain without the amplifier connected to any load, you're really missing the whole point. In a normal RF amplifier, the output or plate circuit is resonated with a tuned circuit that tracks the grid circuit. This maximizes the gain since you have a peaking effect of those tuned circuits. But even an untuned choke in the plate will give a significant gain over a simple resistor. The choke allows the device to have a voltage swing that's up to twice the value of the available DC from cathode to plate. According to Lenz's law, the induced voltage has a polarity or a direction which opposes the change in current that created it. With a radio frequency choke, this approximates a current source that can sustain both positive and negative voltages, again with respect to the plate voltage. So all things being equal, a choke can give twice the voltage swing as a resistor, a simple resistor in the plate. A tuned circuit can give many times that swing because of its Q at resonance. So we have resistively loaded plate, and we can swing basically the plate voltage. We have a choke load plate where we can do 2 times the plate voltage in a swing, and then we have a tuned circuit where we can get several times the voltage available from the plate. So why don't we always tune the plate and grid for these RF amplifiers? Sometimes we do, but getting the tracking right can be difficult between that input and output side of the tube. There's very high impedances that we've created, and they've got to be brought down by tapping or by use of a secondary. Let's not forget that positive feedback occurs, and it can cause instability in a tuned plate, tuned grid oscillator type fashion. So we might have to add neutralization if we have tuning on both sides of the tube. Finally, we don't need to have all of that potential gain. With an input tuned circuit and an output tuned circuit, we might be able to achieve 40, 50 dB of gain. But an RF stage that can provide 10 to 20 dB of gain is usually sufficient to pep up any crystal set. Far more difficult to build a wideband amplifier with high gain and high bandwidth than it is using the same device at a higher frequency with tuned circuits. And we're going to find out why using a narrowband or a tuned circuit with a device allows it to operate at a much higher frequency. The Miller effect. The term Miller effect or Miller capacitance is often seen when reading about amplifier circuit design. It refers to the effective multiplication of the plate-to-grid capacitance in a triode tube by the gain of the amplifying stage. When a tube is amplifying a signal, it has to work against the plate-to-grid capacitance, charging and discharging it as the signal changes. Because the grid is a high impedance and does not sink or source any current, the charge or discharge current must be sourced or synced through the driving source resistance of the previous stage, or in our case, the signal from the antenna. This forms a low-pass filter with a corner frequency determined by the source resistance and the input capacitance from grid to cathode and plate to grid. Back in 1920, John Milton Miller was playing around with some of these circuits, and he assumed that this would be the sum of the two capacitances, so that a low-pass filter would simply be the source resistance against the sum of CGK and CPG, which is C grid to cathode and C plate to grid. But what he discovered was that it seemed to be related to the gain of the stage. So the total Miller capacitance in a triode tube is equal to the plate to grid capacitance multiplied by a factor equal to the stage gain plus 1. The input capacitance of a triode stage is made up of the combination of the grid to cathode capacitance plus the Miller capacitance formed by the grid to plate capacitance multiplied by the stage gain plus 1. The formula for determining the total input capacitance of a triode stage is as follows. Cn equals CGK plus CGP times the gain plus 1, where Cn is the input capacitance, CGK is the grid to cathode capacitance, which is composed of the internal tube cap plus the stray capacitance, and CGP, which is the grid to plate capacitance composed of the internal tube capacitance plus some strays, and A is the stage gain, and it's numeric. For example, let's take a typical tube that we would want to use, a 12AT7 dual triode stage. A typical 12AT7 stage has the following capacitances, and we set it up for a modest gain. CGK is 2.2 puff, plus we're going to give it 0.5 puff of stray capacitance for a total of 2.7 puff. CGP is 1.5 puff, plus 0.5 puff of strays, equals 2 puff. 12AT7 being a high mu triode, we can set the gain at 50. The effective Miller capacitance, Cn, would be 2.7 puff, plus 51 times 2 picofarads equals 104.7 picofarads. Okay, we're going to pick on Matt Renaud's universal tube preamp schematic, and his universal preamp is going to work fine with a 12AT7. So he's got this nice 10K stopper resistor. What's a stopper resistor? It's something you put in the grid that puts some impedance in series. Hey, that's exactly what we need to take advantage of the Miller effect. We take that nice 10K resistor and put it against the 104 picofarads. We come up with the 3 dB down point, or a 3 dB cutoff point of 1 over 6.28 or 2 pi times 10K times 104.7 picofarads, and it comes out to 152 kilohertz. So Matt is effectively limiting his high frequency cutoff so as not to have AM radio stations coming through his guitar amplifier. So now you're saying to yourself, wow, a 12AT7, I thought that was a VHF tube. I thought it was capable of all kinds of gain, and people are using it at oscillators up at 50 megahertz and so on. You're telling me it only works up to a couple hundred kilohertz. That doesn't make sense. Well, first of all, we want to reduce that input impedance. We don't want to use a 10K for RF work. There's several little tricks we can do to help to reduce the Miller effect for our RF circuits. And some of these you already know. Of course, we can reduce the stage gain. That directly reduces the Miller capacitance. We can lower the drive impedance. If you take that 10K resistor down to a 50 ohm, certainly the cutoff frequency would go way out. But probably the most common way that in RF circuits we reduce the effect of the Miller capacitance is by tuning it out with an inductor. Thus, the tuned input tunes out the input capacitance, and a tuned output tunes out the output capacitance, and suddenly the Miller capacitance is not important anymore. We've tuned it out. The other thing we can do is we can use neutralization. If we bring a out-of-phase feedback signal back to the grid of the tube, we can counteract the effect of the charging and discharging of the Miller capacitor. So neutralization is another way to reduce the Miller effect. Okay, so we know we can use triodes, but we have to be very careful with the amount of gain, with the impedances, and let's see why we use pentodes. 99.9% of the time in the front end of a shortwave receiver, you will see a pentode as the RF stage. You will not see triodes. Triodes don't seem to show up until we get to frequencies higher than 30 megahertz. So with pentodes and tetrodes, these tubes don't seem to suffer as much from the effects of Miller capacitance because of the shielding effect of the screen grid, which drastically lowers the plate-to-grid capacitance. Let's consider an old standby RF tube, the 6SK7. Let's say we set it up for a gain of 40. So CGK, grid to cathode, right out of the book is 6 picofarads. We'll give it 0.5 puff of stray, so that's 6.5 picofarads. C grid to plate of 0.005 picofarads, and give it a gain of 40. Therefore, the total input capacitance would be Cn equals 6.5 puff plus 40 plus 1, 41, that's the gain, times 0.005 puff for a total of 6.7 picofarads. So our friend the RF pentode is an excellent choice as an RF amplifier for the shortwave frequencies. It suffers very little from the Miller effect, even at higher gain. At some high frequency, however, the capacitance is present, and noise, even in the best pentodes, such as in the famous 6AK5, which was one of those wonder tubes from World War II radar, or the excellent EF50 or 1852 6AC7 super pentodes. These pentodes simply become deaf at some higher frequency. Triodes are less noisy at VHF and higher frequencies. How are we going to use them? Triodes begin to show up in Miller-fighting topologies, such as the common or grounded grid amplifier. In grounded grid triode amplifiers, the screening action of the grid prevents Miller capacitance and stops positive feedback from plate to cathode. So a lot of times you don't even have to neutralize grounded grid stages. A grounded grid triode can be an effective amplifier at much higher frequencies than a conventional pentode or triode in the normal common cathode topology. Another way to fight Miller effect is to make the gain of the stage lower. How about a gain of 1? That doesn't make a lot of sense since we're trying to amplify weak signals from the antenna, however. Okay, but what if we decide to force the input stage to a gain of 1 by attaching it to a grounded grid amplifier? The grounded grid amplifier exhibits a low impedance. It's a topology that works by amplifying current and turning it into voltage with its output resistance. Think of it as a current to voltage converter, or a low to high impedance device. We call these devices transimpedance amplifiers. So if we now couple the two stages together, the common cathode and the grounded grid, we have produced what is referred to as a cascode, or a cascode arrangement. The word cascode is quite novel. It shows up in the late 20s in a few papers, really unrelated to RF.
Basically, it's the connection of disparate amplifier topologies. In this case, the common cathode to common grid or grounded grid amplifier. If we talk about cascading or cascade amplifiers, that's a whole different ballgame. It's a connection of similar stages, such as common cathode to common cathode, or common grid to common grid, or common plate to common plate. And you have many of them in series. They are in cascade. These cascaded stages were used in radar receivers in World War II. But by World War II, Harvard and MIT began experimenting with the Cascode topology that we just spoke about, both for radar and for VHF amplification. Think of the input stage as a conventional amplifier that, instead of producing voltage, drives current into the common grid stage as its load. The grounded grid stage presents an input impedance of a few hundred ohms. Thus it forces stage 1's voltage gain to be close to 1, and thus the Miller effect is minimized. The grounded grid stage turns the current into voltage and ultimately almost as much gain as a pentode is produced when you put the two stages together. The characteristics of the RF Cascode are quite useful. It has a high input impedance, a high output impedance, high gain, excellent reverse isolation, low noise, and a very high frequency response. The only real penalty is that in the series configuration, where the two stages are stacked and the same current runs down both tubes, the plate voltage is actually split between the two stages. So the voltage on stage 1's plate is usually about 1/3 of the plate voltage, and stage 2's plate is 2/3 of the plate voltage. So you need a voltage of a couple hundred, 200, almost 300 volts to allow for full signal compliance. That is, able to handle strong front-end signals without overloading and to produce full output with no distortion. Parallel configurations do exist. In other words, we could capacitively couple the stages and then put the same voltage on both of them. The price is a few more components to allow for the lower voltage to be utilized. So does the Cascode amplifier ever show up in the shortwave frequencies, or do we only find it at VHF and UHF? It really came into its own with the TVs of the 1950s and early 60s, where the Cascode arrangement was used in just about every TV tuner. But at least one company, Amico, produced a really fine preamplifier with a pair of triodes that worked all the way from 160 meters up to 50 megahertz, 6 meters, and used a pair of Nuvistor triodes in a Cascode circuit. It's the Amico PCL-P preamp. Also, you might remember the realistic DX150 and DX160 series of receivers from the late 60s, early 70s. Those receivers used Cascode bipolar front end and Cascode FET front end, and it was an excellent use of the Cascode circuit in a modern shortwave receiver.
So we're going to be dealing with vacuum tubes in this particular video, and it's probably time to do another little safety discussion on high voltage, high tension, HT, HV, whatever you want to call it. This particular circuit needs 250 volts, so if I just stick my probe in there, I can see I've got 246 volts. That's going to give you a little tickle if you get across that. This power supply is capable of about 50 milliamps. 250 volts with 50 milliamps of capability is certainly enough to give you a lethal shock if you had a weak system, weak heart, whatever. Now, the original voltage coming out of the supply is 340 volts, and we're going through a 6.8K resistor, and it brings it down about 100 volts so that we get down to 250. That tells you that this circuit's not drawing much current, but still, this is high tension, and we have to be very careful around it. So what about safety? Now there is a safety feature built into this breadboard even. I don't know if you can spot it, but you see this back here? This is where the voltage comes in. And you'll notice that it has these ridges on it. Those ridges are to keep your fingers, or a probe, or a screwdriver from accidentally going between the two terminals. And believe it or not, that is a safety feature. So, other ideas. You guys have all seen ideas where you have the plug and the socket, and basically the plug in the socket. And time after time, I'll see people put the socket on the equipment and the high voltage on the plug. You don't put the male side on the side that has the high voltage. If you're feeding power into a circuit, you want the female side to have the juice. Now, as you know, the input circuit on the Cascode is a conventional common cathode. We have a grounded tuned circuit. We have to bias the stage, however. So we have a cathode resistor, which is bypassed, which provides the voltage so that the grid is in the proper place to do Class A amplification. The output is going into the common grid stage, or the grounded grid stage. And we have a little issue, though. The output is basically defined by the resistor in the load of that second section of the tube. And we need to take that high impedance down to a low enough impedance to drive the crystal set. So there were a series of experiments that I did with different topologies using just a simple radio frequency choke was the first approach, with a capacitor going over. So it was a kind of a deliberate mismatch. And it actually gave some gain and worked as a preselector. Very primitive circuit, but it worked okay. I got more gain when I put a 4-to-1 transformer in line. I got even more gain when I put a properly designed 16-to-1 broadband transformer in line. And then I said, oh, what the heck, let's try a cathode follower as well. But the cathode follower did not give as much gain as the properly designed transformer. So that was the evolution of the circuit. So we're actually picking up WWV tonight on the crystal set with the Cascode amplifier. Now I wound another coil. This time I put on 12 turns as a primary and 3 turns as a secondary. So that's 4, ratio of 4, which will give 16-to-1. And this really brought the gain up. Of course, we're increasing the impedance on the plate, and that translates directly into gain. But this broadband transformer idea really came from looking at that Amico schematic. They used a conventional transformer rather than a transmission line transformer. So I thought I'd wind one up. Just for fun, I tuned down to 7.8 megs.
In a place where there's no more need, no more pain, and no more grief.
So what we've done is we have added a cathode follower. And the cathode follower is picking off the point where we have the highest energy, which is the plate of the second Cascode common grid stage. We have the radio frequency choke back in. We're lightly coupled with a 100 picofarad capacitor. And going into a 390K resistor, that could be a 470, a 100K, it really wouldn't make much difference. And then on the cathode, we have a 3.9K. That could be anything from a 1K to a 4.7K, it really doesn't matter. And then the 0.01 comes off that and feeds the crystal set. Now, a cathode follower compared to a properly designed transformer. And we did design a proper transformer that has a ratio of 16 to 1, which is going to be better. Strangely enough, if you do a good job with a transformer, it has almost no loss. The cathode follower, on the other hand, at best it has a gain of about 0.9, and there's some other losses involved with it. So even though the cathode follower is giving more output than the choke through a cap straight in, which is a terrible mismatch, we're basically trying to match several K down to the what we think is a 100 or 200 ohm input of the crystal set. It's of course doing much better than that, but I still think the transformer is giving better performance. You want even better performance? Well, then you'd have to actually put a tuned circuit in the output of the Cascode, and we would definitely have to have neutralization at that point. It would be a much more complex circuit. We would have a 2-gain capacitor and so on. But anyway, I did want to show you that a cathode follower is an option. So, speaking of Cascode, we have 3 different topologies represented here. We have the common cathode, that's the input stage. We have the grounded grid, that's the second stage. And we have the cathode follower, which is a common plate. So we have 3 different topologies in this circuit in a Cascode. They're not in cascade because they're not all the same topology. This goes along with transistors as well. Even if we had NPNs feeding PNPs feeding NPNs, if they all use the same topology, that is common emitter, then they're in cascade, they're not Cascode. However, if we went into a common emitter and then went into a grounded base or a common base circuit, that would be a Cascode. So that's the difference between the 2 terms. Okay, are you pretty satisfied with the tube situation, ready to go on to solid state? The next video we're going to break into the 70s and 80s and explore some of the same types of circuits but using solid state devices.
Don't let that fool you. There really is 60-cycle hum on that record, and it's under the surface noise. We didn't even notice that until we wound up doing the final editing for the program. That one somehow got past them, and they issued it with the 60-cycle hum on it. But nonetheless, it's still enjoyable. But is it Love? Adrian Orlini and his orchestra from July 29th, 1933.